Hi, thanks for the invitation. It's great to be back at the University of Maryland. Always a fun place to come. So I guess I also felt a bit like John in that I wasn't really sure exactly who to aim this talk at. So I just tried to, have it be fairly broad. So probably there'll be something for everyone that they understand, and lots for everyone that they don't understand, and hopefully everyone will at least get something out of it. So let me first begin by wishing happy birthday to the ADS-CFT correspondence. It's now 20 years old. There have been various events celebrating this throughout the year. It's our favorite theory of quantum gravity. Unfortunately, that's not because it's the theory of quantum gravity that describes our world. It's our favorite theory of quantum gravity because it's the one which we're able to at least partially wrap our puny minds around. And that's good. It's sort of the simple harmonic oscillator of quantum gravity. Until recently, though, it's a little bit embarrassing. So most of the work on the ADS-CFT correspondence has really been along the lines of using classical gravity on the bulk side to learn about strongly coupled quantum field theory on the boundary side. There is something to that, right? I mean, we've learned things from doing that, say about strongly coupled plasmas, transport in condensed matter, anomalies, and so on. But it's a little embarrassing because, we're not going to learn anything about the deep puzzles of quantum gravity if we're trying to use this correspondence in the direction of using classical gravity to understand quantum field theory on the boundary. Let me say the same thing in a different way. So we're never going to be able to explain ADS-CFT to computer scientists this way. Now, for the physicists in the audience, you might say, well, okay, that's the problem of the computer scientists. After all, they don't know anything about gravity or relativity or quantum field theory. How are we supposed to be able to explain 21st century physics to them if they don't even understand 20th century physics? Always good to insult your audience at the beginning of a talk. An interesting realization, I think, for many of us, recently for many of us, earlier for smart people like John, is that in fact, we physicists can learn something. Despite this, we can learn something by trying to translate our problems into their language. So the problem I'm going to study today, which is characterizing the holographic map that tells us how things in the bulk, the ADS, are mapped to things in the boundary, turns out to be, just the kind of problem where it's beneficial to try to phrase it in the language of computer science. Today I'm going to describe three features of this map, which, from a sort of physics, quantum field theory point of view, are quite surprising, but which hopefully I'll convince you are quite natural once we learn that we should really think about this holographic map as a quantum error-correcting code, which is something that, at least a good kind of computer scientist, the kind that knows about quantum mechanics, already understands. I heard from Scott that there are some who don't believe in quantum mechanics. What can I say? I just feel sorry for them.
North doesn't believe quantum mechanics.
No, but Tiff believes in quantum mechanics. He just thinks it can't be the whole story. That's different than thinking quantum mechanics is wrong because you don't understand it. All right. So now let me say a little bit anyway more. What is this ADS-CFT anyway, right? So just to get us all on the same page. So ADS-CFT says that if you have quantum gravity in asymptotically anti-de Sitter space, it's equivalent to conformal field theory on its boundary. Now, maybe that doesn't help you, so let me draw a picture. So asymptotically ADS, what is that? That's like sort of gravity inside of the can of soup. So anti-de Sitter space is like the interior of this can. Maybe this is us in the center. Time is going up this way. There's a radial direction going out to the boundary of the can, and then there's some angular directions. And G is not zero, so this is Newton's G. So there's gravity going on here, gravity in a box or gravity in a can. ADS-CFT says that mathematically that's really the same thing, as studying quantum field theory on the boundary of the can. So it's kind of like the soup-can duality. The soup is dual to the can that's holding the soup. And then the very interesting thing is that, the can, the metal side of the duality does not have gravity. So G equals 0. And that's great because gravity is confusing. And so if there's no gravity here and it's the same as having gravity, then maybe we can learn something about gravity.
So is that only for information that it's on the boundary, or is it general?
Well, let me say in a sec a little bit more about how what this arrows mean. Yeah. So this is supposed to be a quantum correspondence. And so what that means is that if I come to you with a state in the Hilbert space of the bulk, then these arrows produce for you a state in the Hilbert space of the boundary conformal field theory and vice versa. So if you like, there's an isomorphism of Hilbert spaces. And moreover, so the states map, so then there should be some statement about the operators also, right? So the simplest thing to say is that the symmetry generators, so for example, the Hamiltonian, the angular momentum, any charges that present on this side also have to exist on that side and, act in the Hilbert space in the same way. So if you like, the Hilbert space decomposes into the same representations of the symmetry group on both sides. So far this is sort of general. So this kind of, this is called sort of giving the dictionary. This is called the dictionary of the duality, telling you how to translate things on one side to things on the other side. So here's the sort of key line in the dictionary that does most of the work. It says if you take a local operator on this bulk side, so remember the bulk, there's this time coordinate and the radial coordinate and these angular coordinates, right? It says if you take a local operator and then you extrapolate it to the boundary by taking this radial coordinate to infinity, so you move it to a point on the boundary, then it just becomes a local operator in the conformal field theory at that point on the boundary. So this is sometimes called the extrapolate dictionary because you extrapolate a local operator in the bulk to the boundary and you get a local operator in the boundary theory. Just to give you, maybe a little bit more intuition, right? So then you can also, in terms of the states, right? So then perturbations of the vacuum, sort of empty ADS, get mapped to low energy states in the CFT. Yeah.
I'm totally confused. I thought the whole point of it was that local bulk operators become non-local on the boundary.
Well, not if you move them to the boundary.
Oh.
If they stay in the center of the bulk, then yes.
Okay.
Yeah. Yes. It's simple for local operators that move to the boundary. Right. Yeah. So then there are low energy states. Those correspond to little ripples on top of anti-de Sitter space. But then if you go to high energy states in the CFD, then that corresponds to large changes of the geometry on the bulk side. In particular, usually it corresponds to creating a black hole. Okay. So that's sort of ADS CFD 101. All right, so now, remember I promised you I would give you 3 features of this correspondence that are surprising to physicists, or at least should be surprising to physicists. So the first is radial commutativity. So I want to remind you that in quantum field theory, causality and locality are expressed by the idea that operators that are space-like separated commute with each other. And that's essential to the consistency of quantum field theory. Day 1 of quantum field theory class, this is what you learn, or at least it's what you should learn. Right. For example, if this wasn't true, then by, I have an operator here and an operator there that don't commute, then by measuring this one, I can change the statistics of what you would get by measuring that one, and that's a telephone for communicating outside the light cone, so that better not be allowed. All right. So we can think about this in the bulk, right? How does locality work in the bulk? Well, so say, for example, I have an operator sitting here in the center of the bulk. So remember, time is going up, so this disk here is a space-like slice of the bulk. So you might think that this operator phi of x sitting in the center of the bulk should commute with some local operator at the boundary of the same slice because they're space-like separated in the bulk, right? In this radial direction, they're space-like separated. But the interesting thing is that that's actually impossible in quantum field theory. It's right, because that would be saying that you have an operator in the quantum field theory, which is non-trivial, this phi of x, Well, it looks like an operator in the bulk, but remember there's an isomorphism. So we push it through the map, and now it's an operator in the CFT. But apparently it's an operator that wants to commute with all the local operators at the boundary. So in quantum field theory, there's a theorem or axiom, depending on who you talk to. As John mentioned, you know, quantum field theory is not a finished subject, so sometimes we can't tell the theorems from the axioms. But whichever way you want to have it, in quantum field theory, if an operator commutes with all the local operators at a fixed time, then it has to be a trivial operator. It has to be proportional to the identity. So if you like, it's an expression of Schur's lemma, which says that an operator algebra which acts irreducibly on the Hilbert space and has something that commutes with it, well, that something has to be proportional to the identity. Yes? Yeah. Yeah, this one, yeah, so that was what I said. So you have to push this guy through the isomorphism and then take the commutator. Yeah. All right, so let me give some intuition for why this is true. So let's talk about something that we all understand, a chain of Pauli spins, a chain of qubits. So if you have a chain of qubits, I don't know how many this is, but 11 or so, well, I don't know, I'm not going to guess. Then the set of products of Pauli operators on these qubits gives a basis for all the operators on the Hilbert space. Right? Hopefully everyone can agree on that. So then that means that if you have an operator that commutes with each of the single site Pauli operators, then it just has to be proportional to the identity. You can't have an operator that commutes with every Pauli but is non-trivial. Right? So if we, using this as a model of the boundary CFT, well, that seems to make it puzzling, right? To think that somehow how did you come up with this guy in the center that commutes with everything? So I should say this, this property, it's sometimes called the time slice axiom of quantum field theory, is a basic expression of the local structure of the Hilbert space. Okay. But clearly somehow ADS-CFT has to get around that. So that's something that we have to make sense out of. Okay, so that's puzzling feature number 1 of ADS-CFT.
So why do you need the extra dimension to emerge so you can go do that transformation from bulk?
Yeah, because I'm trying to say there's a quantum mechanical equivalence between this theory, which lives in, here I've drawn it in 2 + 1 dimensions, and this theory that lives in 1 + 1. Yeah, and if they're the same, then any operator here has to be an operator there. Yeah. Okay. All right, so that's puzzle number 1. Puzzle number 2 is associated to this thing called the Ryu-Takayanagi formula, which hopefully you've at least heard of. You might not know what it is. So let me try to tell you what it is. So again, here's our can of soup. The idea is that, say we're given a time slice of the boundary theory here, which I've indicated by sigma, and moreover, we're given a subregion R of that boundary time slice. So if this is a spin system, maybe this is like, the set of spins sitting over here, some subset of the spins. This R is. So then what the Ryu-Takayanagi formula is it gives a bulk formula for the von Neumann entropy of a state rho in the boundary theory on this subregion R. Right? So if you like, given a state of the spin system, you can compute the reduced state on some subset of the spins, like this R, and then you can compute its von Neumann entropy. And Ryu-Takayanagi tells you that there's a bulk, that's one way of computing it, obviously, but Ryu-Takayanagi tells you there's some seemingly very different way of computing the same thing. So the rule is, given R, what you do is you define this surface gamma R, which is called the RT or HRT surface, which is basically the surface through the bulk of extremal area whose boundary is the boundary of R. So for 2 + 1, it's just this geodesic going through here. And then the rule is that the entropy of rho R is the expectation value of the area of this guy in Planck units, divided by 4g, plus a term which is the entropy in the bulk of the degrees of freedom in between gamma R and R. So that's what's called this entanglement wedge. That's this shaded region here. It's sort of the set of stuff in the bulk that lives between gamma R and R. So it says entropy is equal to area plus bulk entropy. So I can say it again. So the entropy of a boundary region R is equal to the expectation value of the area of the extremal surface in the bulk bounding R in Planck units plus the bulk entropy in this entanglement wedge W sub R. Okay, and so, this is by now almost 10 years old also, and there's, thousands of papers about this. So, so it's, checked many times, certainly true, but it has some surprising features as well. So to me, it's funny people don't complain about this more. To me, this was always one of the big things to complain about. So given that states are dual to states, why isn't entropy just dual to entropy? I mean, isn't that what you would have thought, right? If the Hilbert spaces are the same, the entropy is entropy. Why do we have this area thing here, right? Why is entropy is equal to entropy plus something else, right? And actually, for most of the history of the Ryu-Takayanagi formula, people even just talked about this term, and they didn't even really think about this term. And so entropy then is equal to just something totally different. So why is that? How should that be? Another complaint, so to the extent that this first term is dominant, right, this area term, how is this equation consistent with the linearity of quantum mechanics? Because you see the thing on the left is a nonlinear functional of the state rho, but this is a linear functional of the state rho. So, usually people say this term is small, this term is the leading term, but then how can that be true? Okay, so that's something emphasized by these people. And then finally, well, I said, I guess I was sneaky and I didn't read it out loud, but I said this is true in good states. I mean, come on, right? Like, what are the, okay, so what are the states anyways where it's actually supposed to be true? Okay. And so these are questions which, always bothered me about the Ryu-Takayanagi formula, and for a long time I sort of didn't work on it because I didn't know what to make of these things. Okay, so that's surprising feature number 2 of the correspondence. Entropy is equal to something other than entropy. All right, finally, there's a third surprising feature of the correspondence. Well, I guess surprising is subjective, but surprising to me, which is that there's something called subregion duality, which says that if I give you a bulk operator phi with support in this entanglement wedge W of R, so remember that's sort of this wedge of cheese here in between gamma R and R, then in the CFT, I can represent that operator using, if you like, only the spins in R. So let me draw it from above just to give you a different perspective. So here now I've taken a time slice and I'm just looking at it from the top. So this slice here is kind of like the same as this slice here, looking from above. Right, so then it says that if I have this subregion R here, then inside this wedge here, so here's this gamma R here, and here's R, and I have this region in between. So if phi of x is in there, then I can represent it as an operator using only these spins. But if it's over here, if it's not in that wedge, then I can't. And in fact, I can represent it on the complement set of spins. Okay. So this is something that, I described as evidence accumulated, but there's a lot of evidence for it. It's almost certainly true. In subsets, you can prove it, and actually, eventually, we'll see we can prove it in general. But, this leads again to some surprising situations. So here's a figure which I think I'm contractually obliged to show in every talk that I give. So say I split the boundary into 3 regions, A, B, and C, and I have some operator sitting there in the center. Well, the funny thing is that this operator in the center is not inside of any of these entanglement wedges of A, B, or C, right? Say here's A, the geodesic does that, and so the shaded region is here. But it is inside the shaded region for the union of any 2. So for example, A union B, then I draw the geodesic here, and now it's in between. Or similarly for B union C or A union C. So somehow this operator, well, where is the information? Say I act on the vacuum with this operator or not. I can't get that information from any one of the unions, one of the regions, but I can get it from any 2. So, so where is it, right? I mean, usually, from the point of view of quantum field theory, this is quite surprising. Usually in quantum field theory, we think, the spatial support of an operator is non-negotiable, right? I tell you where the operator is, that's it. You don't get to say, oh no, you thought the operator was here? Oh no, actually I think it's over here. That's not a thing that you usually say in quantum field theory, right? Arthur Whiteman would be very unhappy if I said something like that to him. But somehow ADS-CFT is telling it to us, and then so somehow we have to make sense of it. All right. So each of these puzzles, as hopefully you can see, arises from trying to understand how the bulk physics can be consistent with spatial locality in the CFT, right? Into this structure of individual degrees of freedom at different spatial slices on the boundary. So we can really boil it down to the following question. I mean, how can the same theory be local with two different space-time dimensionalities, right? I mean, it sounds crazy. That's probably the first thing you said when you heard about ADS-CFT, right? This is ridiculous. How can a theory live in 3 dimensions and also in 4 dimensions, right? It seems very clear what the number of dimensions is. And I should emphasize, it's not like string theory where we say maybe there are some extra dimensions that are small. I mean, here they're all big, right? So it really seems like you should be able to tell. But somehow ADS-CFT is telling us, no, you can't always tell. So I think the key point for understanding what's going on here is to realize that this pictures of the bulk, which I've been drawing, which is based on using effective field theory in the bulk, is not valid throughout the Hilbert space of the CFT for any particular bulk observable. And the reason is because if we go to high enough energy in our states, then any particular observable that we're interested in is always going to end up far behind the horizon of some black hole, and will stop being operationally accessible. So when we talk about what the algebras of observables are and so on, who commutes with who and who has support where, we have to realize that we should really be asking those questions in the context of a subspace of the CFT where the observables that we're talking about have a right to make sense. Okay? And then, so now I'll try to convince you. So that's it for the sort of physicsy part of the talk. So now I'll try to convince you that if we think about it from a coding point of view, then we'll immediately see that this radial commutativity and the RT formula, subregion duality, we can just immediately get all of this out in a nice way. All right, and since this is a short talk, I'm just going to do it in the context of a simple model, which, at least some of you have heard me talk about ad nauseum, but it's so much fun, I just have to talk about it one more time, which is the Three-qutrit code. Okay. All right, pivot. Now hopefully info people will start being happier. The Three-qutrit code embeds a single logical qutrit into 3 physical qutrits like this. Right? So it picks out a 3-dimensional subspace of the 27-dimensional Hilbert space of 3 qutrits. Qutrit is a 3-state qubit, in case you don't know. 0, 1, and 2. So this subspace is what's called the logical qutrit. So this subspace, let's just stare at it for a sec. The details don't matter, but we should at least notice that it's symmetric under cyclic permutations of the physical qutrits, and there's a lot of entanglement in all of these states. Now, one way of thinking about this code is we note that about why the code is good is it has this nice feature that there's a unitary transformation that acts just on the first 2 physical qutrits, where it has the property that you can take I tilde, so I runs from 0, 1, or 2, so it's these 3 states. You can get it by just acting with this U12 dagger on a product state where I put I, so I is 0, 1, or 2 here, and then I have this state chi here, which is some maximally mixed state on the 2nd and 3rd physical qutrits. Okay. Now, so what? Why is that interesting? Well, and that's what the unitary is, but don't worry, it won't be on the final. So now the reason why it's interesting is because any logical state, psi tilde, so if you like, psi tilde is just some arbitrary state in this subspace, sum of ci I tilde, one from 0 to 2. Any such state, if I act on it with this U12, then I just map that state onto the first physical qutrit, and then I have this chi sitting there on the second 2. So it means that I can recover all of the information in the logical state from just the first 2 of the qutrits. So the 3rd qutrit is sort of superfluous. It's unnecessary. But the reason why that's interesting is because, by symmetry, there's also going to be a U13 and a U23, and therefore it means that I can recover the state from any 2 of the qutrits, not just from the 1st and 2nd. And so this kind of redundancy should be sort of reminiscent of what we saw in ADS-CFT a minute ago with the 3 regions. Now, in addition to logical states, we also have logical operators, right? So you can have an operator that acts within the code subspace with some matrix elements. Easy enough. And, well, in general, you would guess that to write down one of these logical operators, you're going to have to do something to all 3 of the Q-trits, right? Because the message is sort of entangled in the Q-trits in some way. But actually here, because we have this U12, we can do something sneaky. So we can, well, what we can do is we can sort of decode, and then while the message is sitting here like this, we can just act on the first Q-trit. And then we can re-encode. And that gives us an operator with support only on the first 2 Q-trits, but which implements whichever logical operator we want. And now using the symmetry, you see any logical operator can be represented as an operator on any 2 of the physical Q-trits. So this is reminiscent, again, of this subregion duality. Okay, so now let's make that explicit. So here's the claim. Simplest theory of quantum gravity. The CFT is a very simple CFT. It's a lattice CFT, so I guess it should just be called a lattice QFT. It has 3 sites, and each one is a Q-trit. Here, here, and here. Okay, you thought the boundary theory was simple. The bulk theory, even simpler. 1 lattice point in the bulk, here it is, the blue one sitting there. That's the logical Q-trit, sitting there in the center of the bulk. So then this change of basis I wrote down here is the holographic encoding map. It tells me how to take the states in the bulk and turn them into states in the boundary. And in particular, this correctability we just discussed ensures that indeed we have this subregion duality property, provided, that if we take this picture seriously, we say this point here is inside of the entanglement wedge of any 2 of these, but not inside the entanglement wedge of any 1 of them. So that's pretty good. We got subregion duality out of 3 Q-trits. In fact, we can also do radial commutativity. So we can see that this guy, in the appropriate sense, commutes with all the local operators at the boundary. So let's understand that. So let's look at the commutator of our favorite logical operator. It can be any logical operator. So remember, any logical operator, right? It's just, you can think of it as a field sitting there in the center of the bulk. And now just consider some arbitrary local operator, say on the 3rd Q-trit. So maybe this is the 3rd Q-trit. There's some arbitrary operator over here. So that's like a bulk operator and a boundary operator. We can take their commutator, and we can take its matrix elements between any states in this code subspace. But you see, now we're in business, because O tilde is always acting either to the left or to the right on a state in the code subspace, so we can just replace it by O12. But if we replace it by O12, well then, hey look, the commutator is obviously 0, because O12 acts only on the first 2 Q-trits, and X3 acts on the 3rd Q-trit. But then by symmetry, that would have worked for X1 or X2 also. So now we see that any logical operator of our choice could be very non-trivial, is going to commute with all of the local operators, provided that we take the matrix elements in the code subspace. And so I want to emphasize that it's only because we're working in the code subspace that we're able to circumvent this sort of algebraic irreducibility that we were discussing before. All right. Finally, we can study the Ryu-Takayanagi formula in this model. So first note that any mixed state, any logical mixed state, we can encode like this. So we feed in some mixed state on the first Q-trit. We feed in this state chi, which remember was maximally mixed, on the second 2, and then we conjugate by this U12. Okay, this is just the mixed state version of the same equation I wrote down before, nothing new here. But from this, we can now study the entropy. So remember, from Ryu-Takayanagi, what we want to do is we want to take the entropy on a subregion of the boundary, say 1 and 2 or 3 or something like that. So here, let's do that. So it's pretty easy. So for example, to compute the entanglement, the von Neumann entropy of this state just on the 3rd Q-trit, well, U12 is irrelevant because we're tracing out 1 and 2, so we just have a product state. And then this is gone, and we just have half of chi, which remember was maximally mixed, so there's a log 3. If we go the other way, if we compute the entropy of this state on 1 and 2, well, again, the U's are irrelevant because the entropy is invariant in our unitary conjugation. So again, we just have this product state, and now we get a log 3 from the other half of chi, but then we get the entropy of this state here, but again, that's just the entropy of the whole state. So if we define this area operator, area of the extremal surface operator I mentioned before, to be log 3, then in fact the Ryu-Takayanagi formula is true here. So think about it, right? So here we're studying the entropy, say, just of this guy. So here, so say we have this area here, and then there's no bulk stuff in this wedge. So there's no bulk contribution to the entropy, we just get log 3. That's what we saw here. But now if we do 2 of them, well, now this point in the bulk is in the wedge, so we have to include its contribution to the entropy, and hey, look, there it is. Okay, so apparently the Three-qutrit code also knows about the Ryu-Takayanagi formula. Again, pretty good for a 27-dimensional Hilbert space. All right, and I want to emphasize that the area term comes from the entanglement in chi, which we need to be non-zero to have a good code. So that's the origin of this extra term that tells you entropy is not just entropy. All right, now let me just comment, okay, well, come on, Harlow, what about the rest of the Hilbert space? You promised me an isomorphism, and so far you only told me about 3 of the states. Okay, so, well, what about the other 24, with the other 24-dimensional Hilbert space, orthogonal to the code subspace we've discussed so far? Well, okay, that's fine. So that's where gravity comes to the rescue. So those are the states where we have a black hole sitting in the bulk, which has swallowed our bulk point, and then this 24 is counting the microstates of that black hole.
Wait,
yeah.
Have you given? Sorry. Have you given a general argument for why the Ryu-Takayanagi formula should be kind of like the minimal surface, or is it just because you drew the minimal surface?
Yeah, it's a little bit hard to tell here because the bulk has only 1 point, so it's a bit hard to decide what's the minimal area surface.
Yeah.
In models where the bulk has more than 1 point, then yes, we can derive that. Yeah.
It's like it swallowed up pieces from all 3.
Well, if you like, so the boundary still knows about this. This is still some state in the Hilbert space of the 3 physical qutrits, but it's eaten the bulk qutrit. It's fallen behind the horizon. So when you think about it, for 27-dimensional Hilbert space, it's really pretty good, right? We got local bulk effective field theory, we got Ryu-Takayanagi, we got radial commutativity, black holes with entropy. I don't know. For me, this is the workhorse. Like whenever I'm confused, right? It's impossible to be confused about this model if you think about it for longer than 20 minutes. So everything is clear in this model. Unfortunately, I haven't given you 20 minutes, so that wasn't an attempt to shame you for being confused now. But I promise you, if you think about it for 20 minutes, then you won't be confused.
So I'm a little confused why we need this to be 27 dimensions.
Oh, well, so that's just the question of, that was, why did I pick this code? That just because it's simple. I mean, it didn't have to be. It's just the simplest example. Yeah, Mike? Yeah, so here it's kind of, right, we have to go to a broader family of examples to discuss that. But the moral answer to your question is yes. Yeah.
So if it doesn't, I'm a little confused here. So if it doesn't obey, say, radial locality, you just say that it's behind that whole or is there just a case?
Well, yeah, so the idea is you have to think about the physics. So the idea is that in these states, you would have been mistaken to ask for an operator in the center that commuted with all of the things at the boundary because that observable is gone. So you should only ask for, someone else said this, one of the previous speakers also, right? If you ask the theory for things which you don't need, actually let me quote Ed Whitten, he said this perfectly. If you ask the theory for the things that you don't need, for the answer to questions whose answers you don't need to know, then you're in for a world of pain. So if you restrict only to asking for the answers of questions that you do need the answer to exist and make sense, then you're okay. And so here it's the same kind of thing. So in this state, you could have asked, this thing very far behind the horizon is sort of inaccessible to anyone. So asking for it to commute with everything is kind of too much. Somehow the bulk locality has to break down eventually in the presence of these black holes. Yeah?
There we go.
Oh, okay. All right. All right. Black box. It's okay. All right. So let me now say the conclusion. So here I just gave you some simple model. Obviously, there's got to be more to this story than just this model. And indeed, you can pursue this a lot further using general theorems about quantum error correction. You know, when does the analog of this U12 exist, and so on, to learn more about what kind of error-correcting code ADS-CFT is giving us. So let me just briefly mention a few of the hits, and then, you know, if you want to know more, you can ask me. So one fun fact is that in general, the code has the property that information which is far from the boundary is well protected, and information which is near the boundary is badly protected. So for example, this operator here, I can corrupt just by doing an error that's that big. So it's not a very well protected operator. Whereas this one in the center, for example, if I want to produce an operator that doesn't commute with it, I need to use more than half of the degrees of freedom. So it's a very well protected operator. So, you know, if you want to, you know, protect your, you know, I don't know, codes from the Russians, put them in the center of the bulk. Well, it's hard to get them out of the black hole. You know, it's hard to get them out of the center of the bulk too, but that's even worse. Yeah. Okay, so, you know, we can also study this question that Mike asked about, you know, how big can the code subspace be before the error correction fails? And indeed, you can try to match this onto the regime where in the bulk you expect a black hole to form. So there's some picture. You kind of keep trying to put more and more stuff in here, and then at some point, not anymore, forms a black hole. You can match that onto when the code fails to protect the information. There's a generalization of this Qutrit code, which John and, well, really these two, Fernando and Benny, worked out. John and I were sort of the thought leaders or whatever, I don't know, anyway. Well, that's even unfair. Anyway, okay. So yeah, these guys worked out this nice generalization of the Three-qutrit code where you have a whole volume's worth of degrees of freedom in the bulk. These guys made a nice generalization of this using random tensors, which is really beautiful mathematical physics. So this leads to new codes, you know, codes, even, you know, like, you know, codes like stabilizer codes that, you know, quantum information people like, that weren't found before. You can prove in general that this subregion duality and Ryu-Takayanagi formula are really mathematically equivalent. So any quantum error correcting code has a version of the Ryu-Takayanagi formula, something I thought was interesting, you know. And so, you know, and this theorem that you can prove clarifies various questions about the RT formula. You know, how does it work in superpositions of geometries? To what extent does it hold when there are black holes? You know, once you have theorems that are true, then you can start learning about these things. You know, it's also, from a mathematical point of view, I think that this set of results puts a new focus on the idea of really thinking about operator, you know, von Neumann operator algebras in the context of quantum error correction. And so here are two recent nice things. This one in particular by Brian, I think, is really nice. It's sort of doing an approximate version of operator algebra quantum error correction. So let me just mention, and I was going to sketch the argument, but I think I probably won't because time is running out, especially after the technical difficulties. So, you know, so far this has all been sort of information theoretic, but, you know, this stuff has, you know, nice applications to more sort of traditional high energy physics subjects as well. And in particular, one nice thing you can use it for is to give a proof, and I say new not because there's an old proof, new in the sense that recent. A proof of an old conjecture, which is that in quantum gravity there are no global symmetries, which is a lore that has existed for 50 years. So far, mostly has just been sort of confirmed example by example. But using this machinery, you can make a proof. So a proof is by contradiction, and I can even summarize it on the slide. But I think I won't because time is running out. So let me just close by saying, you know, clearly we're learning a lot from this coding perspective on holography. We may learn more in the future. You know, maybe new theorems in quantum field theory. For example, there's this quantum null energy condition recently proven in part by thinking about these things. There might be new theorems in general relativity. There's some interesting work in progress on that. Maybe more new codes. This one in particular I thought was interesting. So these guys are two grad students from Germany. I don't know how they got into this. But they've made classical versions of holographic codes. You know, so new classical codes based on holography. And so for those, maybe we don't even need a quantum computer. You can use them tomorrow. All right, so thanks.